construction of high-quality roads requires the commitment of large amounts of material and labor combined with good planning, engineering, and construction practices. Modern roads are engineered systems designed to spread wheel loads on stiff surface layers, such as asphalt or concrete, to the much softer natural soil beneath called the subgrade. Layers of intermediate stiffness composed of crushed stone may be included between these layers. The subgrade is often improved through compaction and the addition of one or more soil improvement agents. This video describes how the top of the subgrade layer may be improved through the addition of chemical or cementitious agents, resulting in a stabilized subgrade. The most common material used for stabilizing a highway subgrade composed of clay is lime. Cement and Class C fly ash are also widely used, particularly if the subgrade contains higher fractions of silt and sand and for smaller projects. Construction practices for these three products are addressed in this video. Other products are also used on occasion, such as calcium chloride, cement kiln dust, lime kiln dust, and a variety of petroleum-based products. Lime, cement, and fly ash are shipped as dry materials with a powdery to pebbly texture. All products must be fresh, as exposure to moisture or air will, over time, render the material ineffective. Containers of material used for lab testing should be kept closed when not in use, and fresh material obtained on a regular basis. Material that has reacted with the air may form a surface crust. This material should never be used for test samples. For testing conducted as a part of design or research, it is good policy to confirm the freshness of supplies or to replace supplies on a monthly basis. Safety is a concern when dealing with stabilization materials, as they can be quite reactive. This beaker shows quicklime and water mixed at room temperature. As the water is consumed, the temperature rises to near boiling, causing some splattering. The resulting lime paste is very hot, has a pH of 12.4, and presents a potential burning hazard to the skin and eyes. Fly ash and cement do not react as violently. However, they will react when exposed to water, and appropriate care should be taken when handling them. A pH of 12.4 is required for permanent stabilization of clays with lime and is determined using a pH meter such as the one shown here. Clay soils are the most common candidates for stabilization because of their weak strength when wet and their significant shrink-swell potential. A swelling clay soil can damage pavements through heave and also contribute to pavement damage by not providing the expected subgrade support due to its wetter and softer condition. The addition of lime to this wet, highly plastic clay has two functions. The dry lime consumes some water as it reacts to form hydrated lime. Calcium from the lime reacts with the surfaces of the clay particles, changing the texture of the clay to a siltier, drier soil and greatly reducing the potential for the soil to swell. If sufficient lime is added for true stabilization, bonds will form among the clay particles over a period of weeks and months, greatly increasing the strength of the treated soil. The soil must be wet for these reactions to occur. Therefore, the moisture content should be significantly above optimum for best performance. Fly ash is an industrial byproduct that comes as both Class C ash, shown here, and Class F ash, which is non-self-cementing. Fly ash also consumes water and to some extent may satisfy negative charges on clay particles. However, its primary benefit is that it cements the soil particles together. It is usually used with lower plasticity clays and silts. Unlike lime, it should not be compacted wet of optimum, as this will result in weaker bonding. Fly ash reactions occur very quickly. Due to these quick reactions, the time between mixing and compaction should be kept as short as possible, preferably less than 1 hour, and in no case should be more than 2 hours. There is not the same potential for self-healing of fly ash after the initial reactions are complete as there is for lime, so fly ash treated subgrades are less likely to recover after being damaged. Cement is similar to fly ash in that its primary benefit is that it cements particles together. Cement may be used with any soil. However, the amount of cement required increases as the particle size of the soil decreases. Therefore, cement is more cost-effective when used to treat sandier soils. Compaction should occur quickly, as with fly ash, and water content should be near optimum, as excessive water will result in a more weakly bonded material. A simple experiment illustrates the benefits of soil treatment. This soil was used to prepare samples mixed with lime, fly ash, 2% of cement, and an untreated sample. Consider these treated samples cured for 3 days and then submerged. The native sample disintegrates over a period of several hours, while the lime, fly ash, and cement treated samples remain intact. The treated samples retained a substantial amount of strength after soaking, as shown by the cement sample and by the fly ash sample. The lime sample also retained a significant amount of strength, and it would be expected to continue to gain strength over time. Current practice for Kansas requires that lime be mixed with the water in a slaking tank, shown here, prior to application. Lime reacts with the water and yields a slurry with a very fine particle size. The slurry is transferred to a truck and distributed on the prepared subgrade or added to the subgrade through the mixer. A metering system is used to monitor the rate being applied. This image shows applied lime in the soil after mixing. The soil on the far right has been mixed twice. Here is the same soil 2 days later after the mellowing period has passed and the soil has been remixed. Note the texture of what was a highly plastic clay. Fly ash, shown here, and cement differ from lime as they are applied in a dry form prior to mixing. Current KDOT specifications require that a pressurized or mechanical application system be used that distributes cement or fly ash through a funnel or hood at a controlled rate. A vein spreader is an example of such a system. Typical fly ash application rates are at 10 to 15% of the weight of the dry soil. Depth of treatment in Kansas is usually 6 inches. The fly ash is mixed with the soil and sufficient water is added to meet the target range, typically near optimum moisture. In this case, the water from the truck is being added through the mixer. The resulting mixture will be much drier than lime-treated soils after mixing. Compaction must be completed within 2 hours of mixing, and preferably sooner, due to the fast reactions that take place between the fly ash or cement and the soil. There is no mellowing period followed by remixing for fly ash and cement, as there is with lime. Thorough mixing is extremely important. Mixing reduces the clod size, enabling the stabilizer to come in contact with more of the soil, and also carries it deeper into the subgrade. Inadequate mixing can result in large clumps of soil that remain untreated, and will also leave too much stabilizer at the surface and not get enough to the bottom of the layer. Research has shown that a minimum of 2 passes are necessary to achieve an acceptably mixed subgrade, and that additional mixing beyond 2 passes is beneficial. For lime, additional mixing is conducted after 1 or more days of mellowing. The mellowing period gives the lime a chance to react with the clay prior to final mixing, and the end product has much smaller clod sizes at the time of final compaction. After mellowing, the soil is remixed and recompacted. The soil will then be trimmed to grade and compacted with a flat steel roller to create the final finished surface. Phenolphthalein is commonly used to determine if lime is present in a field sample. Its use is demonstrated here on an untreated soil on the right and a lime-treated soil on the left. As seen on the left, a phenolphthalein solution turns purple when sprayed on lime-treated soil. Phenolphthalein only indicates that lime is present. It is not used to determine the percentage of lime. When digging to test for the presence of lime below the surface, care must be taken to avoid smearing lime-treated soil from the surface over untreated soil below, as this can result in a false positive. Field personnel can go a step further and test to see if the percentage of lime added in the field is adequate by conducting a pH test on a lime-treated field sample to see if the pH exceeds 12.4. Many states, including Kansas, require that a minimum lump size be achieved to verify that sufficient mixing has been done. The current specification in Kansas is that 95% of soil lumps, by weight, pass the 1.5-inch sieve, and 40% pass the number 4 sieve. Lump size is determined in the field using sieve size to fit a standard bucket. Care must be used during splitting and sieving to avoid breaking lumps as a part of the testing, as this could lead to pass rates that are too high. After shaking, the soil on each sieve is weighed to determine the amount retained. Moisture content is determined using the speedy moisture meter, which includes the equipment shown here. For this test, a measured amount of soil, 10 grams in this case, is placed in the pressure vessel. A mixing ball is included to help break up the soil particles. Calcium carbide is then removed from a sealed container and placed in the cap. When the two are mixed, the calcium carbide will react with the water in the soil to generate gas. Therefore, the two are not mixed until the lid is screwed onto the vessel. Mixing takes approximately 1 minute. After mixing, the gas pressure is determined using the gauge on the vessel. The moisture content is determined from the pressure generated. This video has shown the current state of practice in Kansas. Research on soil stabilization is ongoing, and the viewer is encouraged to seek information on the most recent developments.